So imagine, if you will, a little robotic vacuum cleaner, those smart little
Go
things that we have
closer to the
around.
mic, Jesse.
You might need to get the mic.
I'll go ahead and move it over. Imagine, if you will, one of those little robotic vacuum cleaners, right? Sitting in the middle of the room, battery light kind of slowly pulsing, indicating that it's low on charge, sitting probably just a few feet from its charging station, and it can't quite muster the effort and the energy to get back to its charging station. So it seems like it can't quite make it there. We look at it from the perspective of wanting to see ourselves in objects around the world. We look at something like a robotic vacuum cleaner, we don't want to think about it as being lazy. But one of the things that we're challenged with on a regular basis is saying we're looking to replicate our own intelligence in smart devices around us continuously, but we don't quite know ourselves yet. So one of the things that I was challenged with and my team was challenged with as we entered into this Brain Data Bank hackathon competition that was sponsored by the Brain Initiative is a challenge to bring together individuals working in data processing and machine learning and other fields within the paradigm of electrical, data science, and computer processing. And our ultimate goal is to provide something back to the neuroscientists that really are the ones investigating our own brain to begin with, to tell us how to do things like constructing neural networks, better understanding how computer vision is inspired by real vision, generating a more comprehensive view of who we are as entities operating inside of a visual physical world. We can go ahead on to the other slide. It's fine. Yeah, let's just go back to the other slides. Yeah, we'll compensate from here. So I had some animations I wanted to put together, but I'd like to just go ahead and move forward here as we're sensitive on time. The first challenge that we were involved with was a little bit more complex, but this particular challenge being the second challenge, which was started in Zhejiang, China, that we were involved with, dealt with data collected by Dr. Ngora and the team at UCSF. The data sets scale was fairly massive, bringing up sort of a big data type approach to the process. 41 total individuals were included in the original study in the 6-month sample that we analyzed in our first process. But looking at this from the perspective of traveling through time, mostly forward in this case, a follow-up study was done again, looking at those same individuals and their responses at a 6-year period. Now, most of this focused on the ability of older adults to interact with video games and how their brains changed as a result of their interaction with those video gaming platforms, specifically designed games to engage their brains and see how they could improve the efficiency of their mental acuity by training with multiple modalities. So driving at the same time as identifying signs versus just identifying signs, and a no contact control group. So that type of training, often called an intervention within neuroscience, is kind of the factor that we were analyzing. We were attempting to classify the elements that those particular interventions affected within the brain. So how is the brain being changed as a result of this process? Through different visualizations and different processes, traditional visualization yields that there are certain regions of the brain that, even in the initial analysis, weren't targeted as being regions that had changed strongly. Now we were able to make a comparison between the 6-month data and the 6-year data, and we were able to fairly significantly reduce the scale of the data through various processing methodologies. But one of the challenges here, and a challenge that's certainly to be faced in the future, is as we collect more data, as we have more accessibility to the data, storage, scaling, and the storage of processed data is going to become a major issue for all purposes, from the processing side to projecting it back to the user side to creating visualizations. All these things amplify the scale of this data. Our process used focused on putting that raw data, looking at that as the physical world operating as a biochemical phenomena, applying certain filtering and normalizing with a baseline understanding of all subjects, not considering a universal type of approach, not having to understand the entirety of all the data, worked with establishing only a baseline for each user. We then segmented or cut out certain sections, each individual event according to each trigger that was represented as the elements changed on the screen. Then we reshaped the data. One of the things that was a focus was trying to represent and trying to visually represent or process in the same way that we as three-dimensional, four-dimensional beings operate within the world. As we rescaled and reshaped that data, we created a map reconstruction. So we reprojected the data back onto a surface that shape reflected the actual surface of the brain itself. Creating these visualized representations from the mapping paradigm, we fed in sequences of this data as stacks of information. Each slice becoming representative of one specific time step moving forward. But one of our novel elements, and this is an idea stepping forward and seeing how emerging technology and machine learning and data science in general can be applied in a way that had not been previously investigated with neuroscience data of this type, which was to utilize a three-dimensional convolutional approach, spatiotemporal operations, providing features that have an understanding not only of the interactions between the regions of the brain, which are very important to our understanding of analyzing and replicating that network within other paradigms, but in creating technologies that can better help us understand ourselves and better help us create systems to improve our interaction. Now, this particular pipeline allows us to be able to access features based upon interactions between regions, and then apply a simple classification mechanism to understand where each sample at each event, which member group that individual was belonging to, whether they were in the non-contact control, multitasking group, or single tasking group. And the main reason why this matters is because the data collected by Angora and his colleagues there indicated that the multitasking group had larger changes in the total system, better internal neural network coherence, higher efficiency, and better processing. Track back to the little Roomba, we see the efficient system operating within the paradigm. We're nothing if not lazy, and that being a key to one of our core successes in survival is finding ways to amplify and make our own processes more efficient. So stepping forward, one of the things that our particular group sees is being able to take data that's being produced and analyze it in such a way as to provide it back to the people that are utilizing it and getting a benefit out of it as efficiently as possible, and being able to leverage this notion that all this low-hanging fruit is pretty much gone. We now all need to stand with each other, lift each other up as a group, and attempt to access the next era together. Thank you.